All right, today we're going on a trip to what you might call the final frontier of physics. But we're not talking about the edge of the universe. No, this is somewhere way, way stranger. It's a place where the fundamental rules of reality just fall apart. So let's dive into the incredible quest to understand quantum gravity. It all boils down to this one kind of huge question. I mean, think about it. We have these unbelievably successful theories for how giant things work and totally separate but equally successful theories for how tiny things work. But what happens when those two worlds collide? To really get to the heart of this problem, you've got to imagine that the universe is running on two completely different instruction manuals. Two cosmic rule books that, most of the time, just stay on their own separate shelves. So on one hand, you've got general relativity. That's Einstein's masterpiece, right? It describes the beautiful, majestic dance of planets and galaxies. And on the other hand, you have quantum mechanics. And that's where everything gets really, really weird. We're talking about the bizarre, unpredictable world of atoms and particles. Okay, let's start with the big picture. To really wrap your head around general relativity, we need to think about the very fabric of space and time itself. Now, here's the genius part. Einstein realized gravity isn't some invisible force pulling you down. Instead, he said that space and time are actually woven together into one thing, space-time. And this cosmic fabric can bend and stretch and warp whenever there's stuff, mass and energy around. The best analogy, and it's a great one, is to think of space-time as a giant, smooth trampoline. If you put a heavy bowling ball, let's call it the sun, in the middle, it creates this big dip. Now, if you roll a marble nearby, that's our Earth, it doesn't get pulled in. It just follows the curve. It orbits. That, right there, is gravity. So the key takeaway here is that Einstein's universe is elegant. It's predictable, it's smooth and continuous. No sudden jerks or jumps, just these graceful, sweeping curves. But now, we're going to zoom in. I mean, way, way in. Down to a scale where that whole smooth trampoline idea just completely breaks down. Welcome to the quantum world. See, this second rulebook says that on the most fundamental level, everything, energy, matter, all of it, comes in these tiny, indivisible little packets called quanta. You can't have half a packet. It's all or nothing. So with relativity's world is that smooth trampoline, the quantum world is more like a video game, like Minecraft. Seriously. Reality isn't smooth and continuous. It's pixelated. A particle doesn't glide smoothly from point A to point B. It just has a probability of being here, or maybe over there. It can literally just pop from one spot to the next without ever traveling the space in between. It's wild. And that's really the soul of the quantum world. It's chunky, it's all about chance, and it's fundamentally deeply unpredictable. It's the total opposite of the smooth, clockwork universe of gravity. For the longest time, this whole two-rulebook system worked great. Physicists just used one for the big stuff and the other for the small stuff. Easy. But the universe has these extreme places where that neat little separation is impossible. Places where the two rulebooks are forced into a head-on collision. And that brings us to the question that breaks physics. What on earth happens when you have something with an enormous amount of mass, something that creates a huge gravitational dent in space-time, but it's also crushed down into a quantum-sized, impossibly tiny point? And the crazy thing is, these places are real. We're talking about the very heart of a black hole, a singularity of almost infinite density, or the entire universe in the first tiny fraction of a second of the Big Bang. These are the arenas where our two titans of physics have to finally face each other. So what happens when you try to use both rulebooks at once? You're trying to describe a smooth, continuous curve using the rules of a blocky, pixelated game. It's like trying to play chess and checkers on the same board at the same time with both sets of rules. It's just chaos. And here's the punchline. It doesn't just get complicated. The math literally breaks. It becomes nonsense. When you run the numbers, the equations just spit out infinities. The smooth world of relativity and the pixelated world of quantum mechanics contradict each other so violently that our ability to describe reality, it just stops cold. Physics as we know it fails. But a failure like this in science isn't an end. It's a beginning. In fact, it's the beginning of one of the greatest quests in all of science, the search for a single, unified theory of everything. And this quest has a name: quantum gravity. It's the holy grail of modern physics. It's the massive effort to write one single master rulebook that explains how the universe works, everywhere and for everything, from the tiniest pixel to the largest cosmic trampoline. Now, we don't have the final answer yet, but the leading ideas are absolutely fascinating. String theory suggests that maybe particles aren't little points, but are actually tiny vibrating strings. And that simple change helps smooth out all those nasty infinities. Then you've got loop quantum gravity, which takes another path. It suggests that maybe space-time itself is pixelated, made of tiny, indivisible loops, so you can never zoom into an infinitely small point. Okay, so I know what you might be thinking. This is really cool, but it's all about black holes and the Big Bang. Why does this actually matter to me? And honestly, that's the perfect question. Because ultimately, while finding the final theory would be one of the biggest achievements in human history, the real value is in the search itself. This quest to unite our two greatest descriptions of reality, it forces us to ask the deepest possible questions about what space, time, and existence even are. So the next time you look up at the night sky, just remember what you're really seeing. It's a universe with two faces, this vast, smooth, cosmic ocean that Einstein described, and underneath it all, a hidden, buzzing, pixelated world of quantum weirdness. And somewhere, right in the clash between those two faces, lies the next great revolution in how we understand, well, everything. The adventure is just getting started. Makes you wonder, what are we going to find there?